So we were looking at the mass number and atomic number of atoms and what they mean. And we also showed how these numbers could be used to determine the number of each subatomic particle within the atom, the number of protons, neutrons, and electrons. What I didn't say in the last video is that the number of protons for a particular element is always the same. Atoms of the same element have the same number of protons, and that number is unique to that element. So carbon has 6 protons, the atomic number is 6. This number is unique to the element carbon. If we were going from 6 protons to 7, we would be going from a carbon atom to a nitrogen atom. So for the same element, number of protons cannot be changed, but the number of neutrons can. And this leads us on to isotopes. Isotopes are different atoms of the same element containing the same number of protons but different numbers of neutrons. So if there's any confusion at this point, I'll use nitrogen as an example. So nitrogen is the element, and the two atomic symbols shown here represent two different atoms or two different isotopes of nitrogen. Now you'll notice that the number of protons, in other words the atomic number, remains the same at 7, with the only difference being a change in the mass number. And this change is due to the isotope on the right having one more neutron and therefore increasing the mass number by 1. So that's hopefully a bit clearer. But this does leave us with a slight issue, which relates to how we display these elements on the periodic table, specifically the mass number. So if an element has a couple of isotopes, or even several ones, that means they have different mass numbers. Which mass number do we display? For nitrogen, do we display 14 or 15? Well, we actually don't show a single whole number, but rather a number which represents an average of the mass numbers for all isotopes of that particular element. This number is called the relative atomic mass. Now, the definition shown is quite a simple one, and it's not one that you need to memorize. The specification doesn't actually state that you need to memorize a definition, but it is, of course, important to understand what the relative atomic mass is. And it is the average of the mass numbers of all the different isotopes of an element. So when finding the average mass number, we need to find out how much of each isotope exists. So for example, a simple way to understand this would be, let's say we have an element which has two different isotopes, isotope A and isotope B. Isotope A has a mass number of 61, isotope B of 60. Now let's say these are the only two isotopes that exist for this element, and they both occur equally in the world, in nature. If this was the case, which is quite unrealistic, but it's just an example after all, we would have a relative atomic mass of 60.5, exactly halfway in between both of them. But a kind of more realistic example that you might see would be the relative atomic mass number for nitrogen. The two naturally occurring isotopes of nitrogen have mass numbers of 14 and 15. But the vast majority of these nitrogen atoms have mass numbers of 14, which is actually above 99% of them. So a very high proportion. Therefore, the relative atomic mass, which is effectively the average, is 14.007, a number a lot closer to 14 than to 15. Now, if we're provided with the mass numbers of some isotopes and their amounts, we can work out the relative atomic mass through a calculation. And the abundances, which just mean the amounts of these atoms, of these isotopes, are mostly given as a percentage of the total atoms of that element. And you'll see what I mean by this in a minute. But what we do is we have one isotope, and we multiply the mass number of this isotope by its abundance. And we do this with the same calculation with the second isotope, and however many there are. We add these together and we divide by the sum of all abundances. Now, I feel like this is best explained using an example. So let's say we have two isotopes of carbon. One of them, carbon, has a mass number of 12, and the other one, carbon, has a mass number of 13. This first carbon has 6 protons, 6 neutrons, and the second one has 6 protons but 7 neutrons. Now, if we were to say that this first isotope occurs 98% of the time, and the other 2% of the time we have our carbon-13. So the way we would do this calculation is we would look at this first isotope and we'd multiply its mass, the mass number, by its abundance. And then we do the same with the other isotope. Oops. And then what we would do is divide this by the sum of all abundances. So we're basically adding up 98 and 2, which is obviously 100. But if we're using percentages, this number is always going to be 100. You could be in a situation where you're given something like grams instead of abundance, instead of percentages rather, which we will look at. But this is the sum for this particular example that you would write out, and I will show the answer to this at the start of the next tutorial, in which we will look at a couple more examples of calculations like this one.